How do we learn the parameters for naive Bayes? The simplest way to learn the multinomial naive Bayes model is to use maximum likelihood estimates. Simply use the frequencies in the data. So if we're trying to compute the prior probability of a particular document being in a class J, we have the count of all the documents, and out of those, how many of the documents are in class J? That's our prior that a random document will be in class J. For the likelihood, the probability of word sub I given class sub J, we count the number of times word sub I occurs in documents of class J, and we normalize by the total number of words in class J, so the sum over all the words in the vocabulary of the count of those words in documents of class J. So out of all the words in documents of class J, how many of them are our particular word sub I we're looking at? So we're going to compute the fraction of times a word wi appears among all the words in the document of this particular topic C sub j. We're going to do this by creating a kind of mega document for topic J by concatenating all the documents that have that topic together, and then we're going to use the frequency of W in this mega document. So for sentiment analysis, we might have a document sub positive, a mega document for all the positive documents, and we're just going to concatenate them all together into some big mega document, and we might have a document sub neg, and so on. Now, I've been lying to you. We don't, in fact, use maximum likelihood for naive Bayes. And the reason is the following. Imagine we're looking at the word fantastic. We're interested in the word fantastic. It might occur in the test set, but it happens not to have appeared in the training set, in the topic positive, let's say. So the probability of fantastic, given the class positive, in our training set, by maximum likelihood, is the count of fantastic occurring in positive, normalized by the sum over all words of the count of those words in positive. But fantastic never occurs, so that count is 0. So the maximum likelihood estimate for the likelihood of fantastic given positive will be 0. Why is that bad? Because these 0 probabilities can never be conditioned away. If we're looking for the most likely class, that's the argmax over all classes of the prior times the likelihood. And if one of those likelihood terms is 0, then this whole thing is 0, and we're never going to pick that class. The solution is very simple. Add 1 smoothing. So here's the computation without smoothing. And add 1 smoothing, we simply add 1 to each of those counts. So we'll add 1 to the count when it's in the numerator, and every time that count occurs in the denominator, we've added 1 to that too. And we can rewrite that in a form we've seen before, where we're taking the total number of tokens that were in class C, and we've added the vocabulary size, because we added 1 for every vocabulary item into the denominator. So classic Laplace or add 1 smoothing. So let's walk through the calculation of these parameters. First, from the training corpus, we're going to extract the vocabulary, the list of words. Next, we're going to calculate the priors for each class C sub j. So for each class, we're going to get the set of all documents that have that class. We'll call that set doc sub j. And the number of documents in that set divided by the total number of documents, that will give us our prior probability of that particular class. Now for the likelihood, we're going to want to compute the likelihood for every word W sub k given every topic C sub j. So first we're going to create our mega document by concatenating all the documents sub j into a mega document called text sub j. And now for each word W sub k in our vocabulary, we're going to count the number of times W sub k occurs in this mega document text sub j. So that'll be n sub k. And now the probability, the likelihood of word sub k given class sub j is just the add 1 smooth, or I've shown you the add alpha smooth version of the naive Bayes algorithm. So we've added alpha to n sub k, and then in the denominator we have n, the total number of tokens in the class j. What about unknown words? A simple way to deal with unknown words is simply to add an extra word to the vocabulary. We might call that W sub u, the unknown word. And now, what does that do with our likelihood equation? Here's the likelihood equation written out again. We've added a new word W sub u, so I've increased our vocabulary size by 1. Now, what is the count of W sub u in any particular class C? Well, the word was unknown, so it never occurred in our training set, so that count is 0. So the likelihood term for that unknown word is going to be simply 1 over n, that's the number of tokens, in the class C plus the v plus 1. So each of our unknown words is going to be modeled by this very simplistic model of the probability of an unknown word. So learning the parameters for naive Bayes, a simple computation for the prior, and a slightly more complex computation for the likelihood, in which we can use add one smoothing and we can deal with unknown words.